It seems it's working now. I'm Riccardo Scarfone. Today I'm going to present only a part of my research project. Well, actually it's a part of a part, but because in my PhD I started doing constitutive modeling of the hydraulic behavior of unsaturated soils, because we wanted to apply this to introduce, like, to better understand the hydraulic behavior at very low degree of saturation, and including water retention hysteresis. We then implemented this in a numerical code, and which we used to study the basic hydraulic behavior of of capillary barrier systems. And we then moved to numerical and physical modeling of a new concept of multi-layered capillary barrier systems. And now we are, today I'm going to present this part about the numerical study of the applicability of capillary barrier systems for suction control and prevention of rainfall-induced slope instability. Typically, in the ground we can find three different hydraulic situations for soils. So under the water table, typically the soil is in saturated conditions. The pore water pressure is higher than the atmospheric pressure. Above the water table, the conditions are still saturated, just above the water table, but because of capillary rise. And in this case, pore water pressure is lower than the atmospheric pressure, and suction, which we define as the difference between air pressure and pore water pressure, is higher than zero here. And also above this area, now we are in unsaturated conditions. Again, suction also here is higher than zero. Suction has an important role in the shear strength of soils. In particular, typically suction gives a beneficial effect in the shear strength with respect to fully dry and fully saturated conditions. But the geotechnical design typically tends to neglect the effect of suction. Why? Because it's basically unreliable. The idea is that if we have, for example, a slope which is stable because of the effect of suction, after a heavy rainfall, we can have a reduction or loss of suction because of these rainfall events, and we can lose that beneficial effect, and we can have we are losing shear strength, and we can have, for example, slope instability due to this effect. So the idea is, okay, we understand that shear strength, taking into account suction, is not really reliable. But if we find a system able to maintain suction during the entire design life, and we're able to predict the lowest value of suction expected, we can now take that in consideration, for example, for slope stability. And we can improve the slope stability. I'm trying to understand if capillary barrier system is a good candidate for this purpose. So I will give a brief introduction about the capillary barrier system, how they work when in horizontal condition, in a sloping condition. Then we will see a modeling procedure that I adopted to study this problem of the application of capillary barrier system to prevent rainfall-induced slope instability, starting from finite element analysis, using a link code that we wrote to go then to limit analysis. So we will see for the finite element analysis the type of model and geometry, materials, blah, blah, blah. And in particular, we'll focus on the atmospheric boundary conditions, including soil-atmosphere interaction, and we'll see some results. Similarly, we will see the model for the limit analysis and some results as well. We will see some conclusions and some ongoing and future work. So capillary barrier system is a geotechnical system made of an upper finer layer between a sandy silt and a fine sand typically, and overlying a coarser layer between a coarse sand or a gravel, placed over the original soil with the aim of preventing or limiting the percolation of water into the underlying soil. In my case, I'm trying to study this system as a mean to control and maintain suction in the ground, and in this case to prevent rainfall-induced slope instability. The working principle of the capillary barrier system is based on the contrast between the hydraulic properties of these two layers. In particular, the coarser layer is typically a very low degree of saturation, which in terms of hydraulic conductivity means that in contrast with saturated conditions where we know basically that a coarser layer has typically a higher hydraulic conductivity, here at low degree of saturation the coarser layer the hydraulic conductivity of the coarser layer is many order of magnitudes typically lower than the finer layer. This means that when it rains, the water is stored in the finer layer and the coarser layer acts as an impermeable layer. This water then can be removed by evaporation, for example, but if it rains too much and in the final layer we're storing too much water, the suction at the interface may decrease too much, in particular may decrease down to this point, which we call bulk water continuity value, in correspondence of which the hydraulic conductivity of the coarser layer increases dramatically and it becomes basically very permeable to water flow. So the breakthrough from the finer layer to the coarser layer and eventually to the underlying soil occurs, making the barrier fail. If we use a sloping barrier, we identify another mechanism. In particular, when it starts raining, the coarser layer, from the top of the slope, the coarser layer is acting as an impermeable layer. Then this water is diverted within the finer layer of the barrier. And going down to the slope, we reached a certain distance, which we call diversion length, in correspondence of which we reach the water diversion capacity of the barrier. And we're at the interface between the finer and coarser layer, which reach basically the suction corresponding to the breakthrough, so the water continuity value. So what is the modeling procedure that we used in this type of numerical study? We started from finite element analysis using CodeBright, which is a finite element code developed at UPC in Barcelona, with which we performed advanced thermohydraulic simulations, considering multi-phases flows, in particular considering presence gas, liquid, and solid, multi-physics phenomenon like water flow, so water flow in the liquid phase, but also vapor diffusion, and in particular we consider also the soil-atmosphere interaction. Then we wrote a link code in MATLAB that we used to export the suction and degree of saturation contours from the finite element analysis. We created a grid where we interpolate the suction degree of saturation distributions, and we export this to limit state that we used to perform limit analysis. So limit state is a software produced, limit state geo is a software produced at Limit State based in Sheffield, where I recently spent 3 months, which performs limit analysis for geotechnical problems using a discontinuity layout optimization method. It uses a rigid, perfectly plastic behavior, and we consider unsaturated conditions in shear strength using the Bishop model, which is not ideal to represent all the aspects of mechanical behavior of unsaturated soils, but is perfectly adequate to represent the shear strength of unsaturated soils. In particular, we started with the finite element model without the capillary barrier system. We studied a slope 6 meters high with a slope angle of 35 degrees. The soil is representative of the underlying soil is representative of a silt. So the lateral and the bottom boundary conditions are impermeable to liquid and heat flow, but it's not very important because we place them sufficiently far by the interesting zone where basically it's not affecting really the problem. And at the top boundary condition, we applied atmospheric boundary condition that we will see more in detail in a couple of slides. Then we also studied the problem with the capillary barrier system. Here is just a zoom of the central part, where basically we applied a finer layer representative of a fine sand, 40 centimeter thick, and a coarser layer representative of a gravelly sand, 20 centimeter thick. Here I just show the hydraulic properties of this material that we adopted. In particular, the silt was modeled using a conventional Bang & Houghton-Wallen model, but the finer and coarser layer were modeled with a model that we developed to represent better the hydraulic conductivity at very low degree of saturation, which is more important for these materials, where we consider basically, which was often neglected, also the contribution of liquid film, the conductivity of associated to the liquid film covering the grain surfaces, which is important, at low degree of saturation, and we also include water retention hysteresis in all the model. Then, at the bottom of the barrier, we expect to have a drain in reality, where we collect the water coming from the barrier, which in the model we model as basically sink elements which extract water when breakthrough occurs here, so when basically the suction reaches the bulk water continuity value of the coarser layer. So how we model the soil-atmosphere interaction? So first of all, the important parameters. For the atmosphere is temperature, gas pressure, relative humidity, wind speed, rain, and radiation. For the soil surface, so basically the boundary condition in the numerical model, temperature, gas pressure, liquid pressure, and absolute humidity. The two important balances are the mass transfer and the energy transfer. For the mass transfer, we model rain, evaporation. We don't model, at the moment, transpiration. We didn't want to steal the job of the other people who presented before. Then the runoff when suction gets equal to 0. And gas flow. For the energy transfer, we model, we include radiation, sensible heat flux, so advection basically, latent heat flux, so convection associated to the mass transfer of vapor, liquid, water, and air. In particular, we neglect the gas flow in this problem, and we now focus a bit more in particular on evaporation and sensible heat flux. Evaporation and sensible heat flux are represented by these aerodynamic relationships. You can find more in this reference, Broadshire 1982. I will not present all the parameters in these equations, just the important ones. Wind speed, VA, so basically increasing the wind speed, we are increasing the turbulence effect, which are the driving force for the evaporation and sensible heat flux. For the evaporation, we have another driving force is the difference between the absolute humidity of the atmosphere and the absolute humidity at the soil surface, where basically the absolute humidity is the mass of vapor over a unit volume of moist air, where they are function of the atmospheric one is a function of atmospheric temperature, gas, and relative humidity. At the soil surface is a function of temperature, gas pressure, and liquid pressure, which is in particular governed basically by the psychometric law. Here there's like a quantitative diagram how the absolute humidity at the soil surface depends on suction, and so the evaporation. You can see that basically the soil at a fixed temperature, the soil, the absolute humidity at the soil surface decreases with increasing suction, and at the beginning this difference is high between the absolute humidity at the soil surface and atmosphere, which means the evaporation rate is high. When the suction, when we are drying out the soil surface, the evaporation, this absolute humidity at the soil surface decreases, this difference decreases, and the evaporation rate starts decreasing. So in general, starting from a wet surface, when the suction is low and the degree of saturation is high, we have a fast evaporation. When it starts drying out, the evaporation, so suction increases and degree of saturation decreases, the evaporation rate is low. Similarly, in this other relationship here, the driving force is the difference between the temperature at the soil surface and the atmosphere. Okay. So how we model the weather conditions? We consider a specific site, Cagliari in Italy, where we had measured data of air temperature, relative humidity, radiation, and wind speed in these 30 years, 1981-2010. We elaborated the data, and we fitted the data over the year, basically, using a sinusoidal yearly distribution of these different parameters. What we do with rain is a little bit different. So at the beginning we do the same story. Basically, we consider 3 steps for our analysis. In the first step, lasting 20 years, we are initializing the hydraulic conditions of the underlying soil. So we are getting realistic hydraulic conditions using this type of distribution, using the same 30-year period. We do the same now in the second step with a 10 years period, but now initializing the hydraulic conditions of the capillary barrier system, using still a nearly sinusoidal distribution of rainfall when there is the capillary barrier system. In the model where we are not considering the capillary barrier system, it's just another 10 years as the first period. In the third step that we are interested in, basically we are analyzing the response of the system to a very wet 10-year periods, where now we consider daily distribution of rainfall from 1984 to 1993, which, as I said, it was quite a wet period for the site. And in particular, we will see results over the 10 years, but in particular, we will focus on the most critical rainfall event occurred in the 7th of March, 1995. So, starting from the finite element result from finite element analysis, here is the degree of saturation contours in the most critical rainfall event without the capillary barrier system and with the capillary barrier system. This red color means that at this moment, the soil here is fully saturated. Here, this is a sharp wetting front. Whereas, when we consider the presence of the capillary barrier system, as you can see in correspondence of the capillary barrier system in the most critical rainfall event, the soil basically remains more or less relatively dry, so with a degree of saturation around 0.3. Whereas outside the barrier is following the same story as above. In particular, if we are also interested in the suction profiles, considering the different sections with colors and with the lines corresponding to the both colors and solid lines correspond to the case with the capillary barrier system, and the dashed line correspond to the case without the capillary barrier system. We can see that in the most critical rainfall event, basically the presence of the capillary barrier system allows to maintain much higher value of suction corresponding to the absence of the capillary barrier system. In particular, in absence of the capillary barrier system, we see that we reach basically, zooming this part here, we see that the suction close at the surface basically reaches zero, a value of 0, and is around a few kilopascal, like until 5 in the first 80 centimeter of the underlying soil. Similarly, if we plot the time histories of degree of saturation suction at this midpoint at the surface of the underlying soil, we see how, using the capillary barrier system, we are, with the red curve, we are able to control the degree of saturation, which stays always low, whereas during winter, without the capillary barrier system, it reaches very high value. Similarly to suction, here I just show a zoom of this low value suction. We see how the presence of the capillary barrier system, red curve, is able to control the minimum value of suction attained during the entire life during this 10-year period. To understand how it works, the barrier, how it's acting, actually I already gave you some idea in the introduction. We show here the liquid velocity and degree of saturation contours, where we can see that basically the idea is that the water is diverted in the finer layer, as we can see in the degree of saturation and in the liquid velocity contours, and also here where we are plotting degree of saturation and velocity profiles in the barrier at this different section. As we can see, basically the water is going down the slope. Basically more and more water is diverted. This water is then removed at the bottom of the slope by the element, the drain elements that we place there. Now we go to the limit analysis. We consider three cases: a case without the capillary barrier system, a case where we consider the capillary barrier system and we're analyzing the stability of the overall system, so including the barrier, and then a third case where we consider the effect of the presence of the capillary barrier system, but only on the stability of the underlying soil, to understand only, to isolate a bit the effects. And here, the fine sand and gravelly sand have, so I'm considering cohesionless soils, and fine sand and gravelly sand typically are more have a higher friction angle. Silt typically is a bit low, so 40 degree and 20 degree for the silt. Factor of safety for these cohesionless soils we are considering as the ratio between the tangent of the characteristic friction angle, so basically this, and the friction angle which would cause the collapse in the limit analysis. Here we can see on the left the result in the most critical rainfall event. You can see that without the capillary barrier system we develop quite a shallow mechanism due to the presence of that saturated zone, where the factor of safety is lower than 1. So basically we would have had the slope instability in this case. Whereas when we place a capillary barrier system, first of all, let's look at the stability of the underlying soil with the effect of the presence of the capillary barrier system. The factor of safety now is extremely higher, like around 80. And now the new phenomenon is just we have to focus on this instability of the capillary barrier system, but this because the material which typically form the barrier have higher friction angles typically. The factor of safety now is higher than 1, so the barrier is stable now. Here, same story, we are now plotting the time history of the factor of safety for wet critical event for every year, where we can see a similar picture that I described here, and in particular you can see like the stability of the barrier is quite more or less constant during these critical events, which means that actually the stability of the barrier doesn't really rely on suction, but just on the material strength itself. So in conclusion, numerical methodology to link advanced coupled finite element thermohydraulic analysis, where we included soil-atmosphere interaction to limit analysis, was developed to study developed and applied to study the long-term performance of the barriers, capillary barriers applied to slope stability. And finite element analysis suggests that a barrier is able to collect rainfall water, which is diverted in the finer layer to a drain placed at the bottom of the slope. In presence of the barrier, the degree of saturation in the underlying soil remains constantly low compared to the case in absence of the barrier, and the consequence is the minimum suction values that we obtain with the presence of the barrier are increased compared to the case without the barrier. Finally, the limit analysis suggests that the presence of the barrier may be highly efficient in preventing rainfall-induced slope stability for the case we studied, and the problem becomes then controlled by the stability of the barrier itself, but this is typically made of material with high higher strength, so higher friction angle, for example. This was only a picture of the work I'm doing on this part. So the idea is extending the only picture I gave you here to more parameters, to understand the influence of other parameters, where we analyze the influence of weather conditions, for example, for a wetter climate, the geometry of the underlying soil, considering other slope angles, and the slope height. In particular, if we increase the slope height, we end up in a situation probably where we have breakthrough before we collect water at the top, the bottom drain. So we are considering to insert multiple drains along the different heights of the barrier. We consider different geometry for the barrier thickness of the layers, and also multi-layered capillary barrier systems, and finally the different materials for the final layer and the underlying soil. Thank you for the attention.